with Hydrop, and I'm lucky enough to lead their process and R&D effort. And welcome to this morning's session on pre and post digestion. Hope you all enjoyed the delights of Newcastle last night. Good? Good. So time's going to be pretty tight, so we're going to press on quickly between each presentation. And without further ado, I'd like to introduce our first speaker this morning, Ross Byron of United Utilities.
Thanks, Jeff. Morning, everyone. As Jeff said, my name is Ross Byron. I'm a graduate process engineer within the process engineering team at United Utilities. And today I'll be talking about the dewatering trial that we've done over around the last 12 months, talking about the performance and operation experiences of United Utilities using the volute technology. So a little bit of an overview of what I'm going to go over. So do a little bit on the project background, kind of the main partners and who's been funding it, and kind of the objectives of the trial. Then I'll do a little bit on the overview of MBC, which is where we located the pilot plant, and then talk about the setup of the rig itself and the technology. And then I'll move on to the two trials that I'm going to talk about. So I'll go through the objectives, testing methodology, and the results of both the digested sludge trial and the raw sludge trial that we carried out. And then just to wrap up, I'll do a bit of a summary of the results, the operational experiences, and then the further work that we're looking to undertake at UU. So first of all, a little bit of background on the project. So two partners on the project team essentially is United Utilities and Evergreen that work to design and operate the solution at MBC. And then we've got the Industrial Energy Efficiency Accelerator funded by the Department of Business, Energy and Industrial Strategy and managed by the Carbon Trust with the support of Jacobs. So the main real objective of the trial is to test the volute dewatering technology at pilot scale at one of our sites, which we chose to be MBC, which is a part of Davy Hume Wastewater Treatment Works, and really compare it to the on-site centrifuges that we've got there in terms of performance with kind of a comparable feed sludge and doing sampling alongside that. So a little bit on the Industrial Energy Efficiency Accelerator. So it's a program that aims to seek out kind of low carbon and energy efficient technologies funded by the Department of Energy and Business, Energy and Industrial Strategy. So that really drove one of the main objectives of the trial, which was to reduce the energy consumption of dewatering technology. So the initial aim of the trial was to get a 70% reduction in energy cost and energy consumption compared to the centrifuge. So that's kind of one of the main metrics that we'll judge the trial by, and one of the main reasons that we got the grant funding for the project. So a little bit of background on MBC itself. So not to go into too much detail, as you're probably all very familiar with a kind of standard TH plant. But in terms of the raw sludge feeds that we used, or the sludge feeds to the volute, the first one there is the raw sludge. So a combination of the indigenous primary and liquid imports from various regional satellite sites, combined with kind of thickened SAS through a drum thickener. And obviously that goes through the TH process, digestion, and then brings us to our second feedstock, which is the digested sludge. So comparing directly with what the centrifuges will be doing. So we've got comparable trial, and it's kind of a fair assessment of the technologies. So it's a little bit of an overview of the rig that we've got itself. So we've got it set up, as I said, at MBC at Davy Hume, and it's a 40-foot shipping container that contains all the kit. So I guess going left to right there, you can see on the bottom left picture, you've got that blue and red pipe going in. So that's essentially the feed from our buffer tank that feed the various feed sludges that we had throughout the trial, that we hooked up to various points of the sludge treatment centre. So it goes into there through the wall, and then on the back wall, on the right-hand diagram, you've got a schematic, which is the feed pumps, and then coming along that back wall, you've got the flocculation tank, the volute screw press itself, and then you've got the conveyor coming out towards the skip on the left-hand side there as well, with the filtrate falling through the bottom and going into a filtrate tank to be pumped back to site centrate. And then again, on the kind of the top side of the PFD and the left side of the picture, we've got the poly IBCs, which again is pumped through into kind of the near side next to the door, where we've got the poly day tank, which then feeds the poly makeup system to dose whatever concentration of polymer we want. So we dose the polymer into one of two places, either the feed pipe where the pumps are, or into the actual flocculation tank itself. And the flocculation tank was quite well put together in terms of doing a trial of this kind, because we had a perspex screen on the top where the operators could really see the effect of polydose in terms of flock size, and really be able to fine-tune the operation quite well with that, and getting to know it over time. So now, a bit of an overview on the technology itself. So I didn't really mention the volute itself in that little overview. So I'll start on the right-hand side there. So you've got a little bit of schematic of the actual inner mechanism of it. So you've got the screw in the middle, and then you've got the ring coming around it as well. So you've got two different types of rings. You've got the fixed and the moving ring, which alternate kind of one after the other along the axis of the screw. So essentially the fixed ring is fixed, and then the moving ring kind of moves up and down concentrically to squeeze the sludge and compress, get the compression pressure to squeeze the water out of the sludge. And in terms of those two, looking at the left-hand side now on that schematic, we've got the thickening zone and the dewatering zone. The difference between those is just the gaps between the rings. So in the dewatering zone, you get a higher compression pressure, so you can get the last few percentage of water out of the sludge. In terms of where you get most of the filtrate out, you get most of it out in the thickening zone in the first kind of half of the screw, and then towards the end you just get the last bits of it, which ends up kind of producing a little bit of a dirtier filtrate than the thickening, but I'll mention that a little bit later on. In terms of the levers that we can pull into looking at this diagram, so we've got the screw speed itself, so we can speed that up or slow that down to I guess increase the residence time and modify the throughput and dry solids relationship. And then we've also got the end plate gap there at the end, so similar to the screw speed, we can push that closer towards the end of the screw to increase the compression pressure and increase dry solids, or conversely we can move it out to allow us to get more throughput but potentially lower dry solids. So now moving on to the first trial itself, so talking about the sludge trial, so directly compared with the dewatering centrifuges on site. So again, just talking about the main objective and what we compared directly on site through sampling and collection of data on the PLC. So we were looking at directly comparing the OPEX of the on-site centrifuges for the same sludge feeds. So first one is cake dry solids. Obviously, that's quite heavily linked to transport costs. Power and poly, they're obviously quite your obvious direct OPEX. And then you've got filtrate quality as well, with kind of the new charging methodology coming in the future. I thought it was important to include that as well. And then a more qualitative assessment is just the operability of it and our general impressions of how easy it was to operate and how the operators managed to optimize and get the best out of it. And then again, looking at kind of the levers that we can pull to optimize, throughput was one of them. So obviously, in terms of the methodology of the trial, we kind of progressively increased the throughput and tested various different polydose rates, but obviously different setups of these variables here to kind of drive a better overall kind of throughput and product to drive the whole life cost. Second one, polydose rate. That's a fairly obvious one. Obviously, increasing the poly, we tend to get high dry solids. End plate gap, mentioned that in the last slide. Could modify that to get more throughput or potentially high dry solids if we increase the compression pressure. Flock tank agitator, obviously that's all to do with the poly as well, and getting that fully mixed and making sure we're not over or underdosing poly. And then again, screw speed, so that's kind of linked to the throughput as well. So now onto the results of the digested trial. So I thought I'd just flash up a picture, first of all, of the cake itself. So we got pretty good, well, very good results on the cake throughout the trial. It was quite a good quality cake as well in terms of sending to land. Our agricultural services team and the farmers were more than happy to accept it. It was as good, or if not better, than the centrifuge cake that we were getting off as well. So in terms of the product throughout the trial, it was very good in terms of stackability and general cake quality. Now, these two graphs, I guess, kind of illustrate what I was talking about in the testing methodology in terms of how we went about increasing the throughput and modifying the polydose. So we tended to, I guess, look at a range of polydoses initially and then kind of filter out by kind of the general results of kind of how it was going on site, and then we'd kind of get a smaller range of polydoses to try for a longer period. So it's not particularly surprising, but in terms of the filtrate quality, you can see as the polydose was increased, we got slightly better filtrate quality down towards around 1,000 milligrams per litre. And then again on cake quality, a similar trend there. If you look at the 1,000 kilos dry solids an hour, you can see that as we increase the polydose, we get a better cake. And just linking into, I guess, one of the main objectives of the trial, which was the power consumption. So you can see the specific power of the volute for the various different throughputs. We were sitting around the 3.8 to 4 kilowatt hour per ton, and I suppose for reference, the centrifuges on site were consuming around 25 kilowatt hour per ton, so it's quite a marked difference in power consumption. And I probably should have mentioned that mainly due to the speed of the screw turning. So the centrifuges run at about 1,500 RPM, whereas the screw in the volute runs about 1.5 to 2 RPM. So it's a massive difference in terms of that. So looking at a little bit of a mass balance of both the centrifuge and the volute. So in terms of, I guess, the cake quality, the cake dry solids and the filtrate, so the centrifuge performed very slightly better, but in terms of looking at that from a cost perspective, the margin's so small that the cost was pretty negligible in terms of haulage costs. Looking at the direct OPEXs, you can see there that overall the volute is slightly superior, driven by the massive, the around 85% reduction in the power cost, which is again due to the speed of the screws turning. So that's the digested trial. Moving on to the raw trial, so comparing to the thickening centrifuges now, which has got the primary liquid imports and the thickened SAS. So again, same objective really in terms of the OPEX. Obviously, the cake dry solids has got different kind of applications in where we'd want to be with the volute on the raw. For instance, if it was at a satellite site, then we'd want the dry solids as high as possible for haulage. But for instance, for a Canby, we're not particularly not particularly bothered about getting up to the kind of the 28 and 30%. But the volute flexibility allows us to do that with the levers we've got, such as the end plate gap and the screw speed. So in terms of the different OPEX factors, it's essentially the same. The variables, again, it's the same pilot rig setup, so exactly the same variables that we've got to play with. So in terms of the raw trial results, this is a similar graph to what you saw in the last one, and we kind of found with the raw sludge that once we got up above a certain point, with being the kind of 3 kilos per TDS polymer dose, we didn't see huge improvements in the dry solids in the cake, so it allowed us to kind of dial down the poly a little bit to kind of save on that in the OPEX. So again, showing you the same graphic as like the last one, but for the raw sludge trial. So you can see that the volute actually is a little bit better in terms of comparing directly on the cake dry solids and the filtrate quality, which obviously translates to a saving on OPEX. And then looking at the direct ones that I've got there on the bottom, power and poly, you can see quite significant savings in not only the power, but also the poly as well, which drives a nice saving on the TDS, pounds per TDS. So that's both the trials that we've done so far over the last kind of 12 months or so. So I suppose as a bit of a summary of both of those results, you can see that the OPEX for the volute compared to the centrifuge is very, very competitive and superior in some instances. So overall, it's competitive in terms of OPEX. And looking to do further work on that as well, to incorporate kind of filtrate liquor charging methodology as well. In terms of kind of operational experiences, we found as well that the volute was really good at handling low dry solids feeds. More so, kind of the centrifuges struggle a little bit when when the feed quality drops, but the volute was pretty good with low feed dry solids and could accept quite a bit of variation in that. Flexible from a maintenance perspective as well. So the containerized nature of the solution obviously it took quite a bit of work in the initial design phase, but kind of the accessibility and the flexibility in the maintenance we've got is really, really good for a containerized solution, and we can take the rig pretty much anywhere we want to and kind of install it there for a period which we're looking to do in the future. And then I suppose just a bit of a nod to some of the commissioning issues we had, which were overcome eventually, but we had some small issues with the flow distribution, which were kind of quite quickly corrected with some mods to the optimizations to the variables that I've mentioned earlier, in particular the flock speed agitator and direction. So looking at further work that we've got on the horizon, so quite a big one is looking at the dewatering zone filtrate. So I mentioned earlier that that filtrate is quite a bit dirtier than the thickening zone. So towards the end of the trial, we started to recirculate that dirtier filtrate back to the flock tank to get a superior overall filtrate, and it worked quite well. But obviously we've got a bit more data that we need to collect for that, and obviously there's could be potential other benefits, not just the filtrate quality. If there's some poly in the liquor as well, which there shouldn't be huge amounts of, but every little helps, I suppose. So we could see benefits there as well. Next one is SAS thickening to 16%. So thinking back to the PFD of MBC that I showed earlier, we would look to use the volute to thicken from kind of the 0.8% of SAS up to kind of 16% to feed to the cambio, which would eliminate the drum thickener that we've got on site and the centrifuge as well. So that'd be a big cost saving and an OPEX saving as well. And then finally, looking towards the future now, really looking to kind of nail down the TOTEX and understand where exactly in terms of scale we can deploy the volute, and looking to use the pilot rig that we've got now and deploy that elsewhere as well in the business to realise cost savings and in particular energy savings. And I suppose just to conclude, I suppose the main objective of the trial was to get the 70% energy reduction, which is what we got the grant funding for. And I suppose from those results there, you can tell that we kind of achieved that, and the energy saving that we got was around 85% overall across both sludge trials. So very positive there from, I guess, the trial objectives point of view, and promising as well in terms of the general operability and general opinion of UU around the volute and where we can deploy it. So that's everything I've got. So hand back over to Jeff for questions.
Okay. Thank you, Ross. I can truly say it is a great piece of kit because I was involved with the first UK installation in NIG. Any questions for Ross, please?
Well, thank you. Yeah, Neil Willoughby from Meliquor Hydroc. Great presentation. I was also involved with the volute as well. It is a good bit of kit. Does that mean that you can now replace all of the centrifuges and all of the drum thickeners at Davy Hume with the volute?
Potentially, obviously, throughput is a bit of a challenge, but with kind of new models that Evergreen bringing out, that kind of throughput issue is becoming less and less. In terms of the SAS thickening, it is a trial that we've got to do and kind of get the results and to see if we can get to 16%. But in terms of replacing the thickening, the dewatering, the results that we've shown are really good and show that it's very much comparable in terms of quality of cake, filtrate, and OPEX as well.
Anybody else?
Hi, I'm Daniel from Hack. Basically, initially showed the volute, and I haven't personally seen it, but you had a thickening stage and a dewatering stage, and you're also talking about replacing your digesters as well as your centrifuge as well as your thickeners with the volute. But what I want to understand is, would you need a separate volute for like the thickening process and a separate one for the dewatering process, or is it capable of like this just doing both in one volute basically? So can you have two discharge points because you had the the dewatering side and the thickening side, if you see what I mean.
Yeah, so I'm not aware of them splitting up the thickening and dewatering zone. As far as I'm aware, those kind of come as a package really, yeah, I suppose in terms of can it do it, again, it's something that we're looking at for the SAS, but we don't really separate the thickening and dewatering zone. It's just the ability to separate the filtrate really is what we look at in terms of those zones, because it's quite a marked difference between the quality in those different zones, because you get most of the filtrate out in the thickening zone, and then the dewatering zone you get a little bit of filtrate out that's kind of much worse quality. So that's kind of the benefit of separating it into those zones.
Okay, so if you were going to get one for the thickening process, you need a separate volute for the dewatering as well as a separate volute for the thickening side.
Yeah, so in MBC we'd essentially replace the thickening centrifuge with a volute, or if we were looking to go SAS to 16%, we'd replace the drum thickener and the centrifuge, and if we were on the dewatering centrifuge, we'd just replace that with a volute as well. Yeah.
Right. Thanks.
Time for one more question if anybody has one. In that case, can I ask what water use there is associated with a volute?
It's a good question. I don't know that off the top of my head, Jeff, actually. I can get back to you on that.
All right, go on.
I can give you an impression if you want.
Yeah.
Robert van Leemen, Amcon Europe. Fully disclosure, we're producers of the volute. That's why. Now, if we keep the standard shower settings on this thing, then on the size that was used for this project, we would use around 150 liters per hour.
Thank you. Okay, thank you very much, Ross. We're getting both of you? Yeah, please. Okay, so next is Dale Foster, who I've known for many, many years, unfortunately, and Jason Sims of Huber. So please take it away, gents.
Yeah, thanks, Jeff. There's plenty of familiar faces in the room here this morning. Yeah, Jason and I we've teamed up and put this together. Over a few beers last night, it was decided that why am I really doing this presentation? He did the trials. But I'll echo what Ross was saying about the importance of trials. And Jason's been heavily involved over many, many years, trialing all sorts of our equipment. So I'm going to hand over to Jason now, and he's going to take you through it, but I'll hang around for any questions. Thank you.
See, that's why he's on the big money. Yeah, thanks, Dale. The main focus of the trial was to really investigate the dewatability of a fairly uncommon sludge, a coldness sludge. The main driver that Anglian Water were looking at was they were spending a small fortune on exporting 6 28-meter cube loads of this. That wasn't me. They're exporting loads of thickened sludge from Corby WRC every week, and clearly there's a potential cost benefit if they can dewater that on site and transport it to a cake reception facility on another bigger site. Because at present they've got gravity belt thickening, which does what it says on the tin, but clearly there's potential savings there. And we've built up quite a good relationship with Anglian Water over the last few years. We've been doing a lot of S-disc and S-drum sludge thickening installations with them. So that's why they came to us for a trial. So from the customer's perspective, they were looking at the dewaterability of this pre-thickened sludge, and in particular the required polydosing rate to do that if it is achievable. Whether there is a reduction in this sludge in order to carry out dewatering, because as you'll see from the following slides, the the product from the gravity belt thickness is particularly thick. And at the time, at the time of the trial, it really was particularly thick. And in terms of achievable cake characteristics, we're not just talking about the dryness, although as far as AW are concerned, they weren't looking for a specific dry solids content. They just wanted it to be stackable. But also they were looking at things like odor and things like that. So in terms of ideal outcomes, yes, it needs to be stackable, but above 20% dry solids would be nice. Active poly dose requirement less than 10 kilograms per ton of DS would be nice as well. And really, if they could get away with no additional mixing or dilution of that pre-thickened sludge, then obviously that's a win as well. So Corby treats a population of nearly 20,000, dry with a flow of just over 200 litres per second, full flow treatment of just over 500 litres per second. And there aren't any major industries, although there are some food manufacturers nearby as well, but they don't have a significant input on the loading rates. And in terms, I'm going to have to get used to that, aren't I? So the site produces roughly 320 metres cubed per day of, it is technically a primary sludge, but it's nothing like the sort of primary sludges most of you will be having on your sites. The Kalna sludge is produced from a moving bed biofilm process, which use aeration and these little K1 carrier media. As on the picture on the right shows, that's the biomass building up in it. So in terms of characteristics, it's quite like a secondary sludge. And without going into detail, I think the phrase that was used was, it can be challenging to process in terms of the sites that have to receive this stuff. I know it's going to go forwards. In addition to the caldness, it's also producing SAS on site as well, close to 200 metres cubed per day. However, they do manually decant that to get rid of a significant water proportion, and that decanted SAS goes onto a settlement resulting in around 100 metres cubed per day of it. Both sludges are pumped across into a tank, which does have a recirculation pump, but that never really gets used. That's just a decision on ops. I would like to think it's because they want to reduce the carbon footprint, but it may be down to other reasons. And typically, when the decanted SAS is pumped across in the morning, the tank is then topped up with caldness as the day progresses. So that does mean that the ratio between the two sludge types does vary throughout the day, which, as you can imagine, would potentially have impacts on any trial that you're doing. However, the combined sludge is then thickened via one of two available gravity belt thickeners. One is fairly recent installation, but the other's a bit of a dinosaur. So you've got to take that into account if you were doing any sort of analysis between the existing technology and putting something else in. It's by no means look, here's the best gravity belt thickener installation versus this. There's old technology that we're comparing against. The new unit runs continuously, and the other is only really used if there's a backlog of sludge, or if the other new unit is offline for any reason. And typically, the duty unit is running around 20 meters cubed per hour. We didn't feel it was our place to give away the customer's site running cost, but a cost analysis per annum was undertaken. And as I say, although historically the GBTs produce 4 to 6% dry solids, during the trial it was between 6 and 8%. So that did make things a little bit interesting for me in terms of running the actual trial unit. They use up about 1 meter cubed IBC of neat poly every 3.6 weeks. So the plant is forecast to use around 50 meters cubed in a year. And in terms of all the ancillary items that you'd look at in terms of power usage and the like, the only real technology-specific drives related to the gravity belt thickness are the roller drive and the wash-water boosting pumps on both units. So there's our little 20-foot container. It hosts the smallest of the cube press range. Now, we made a conscientious decision not to add slides about how the technology works, because we've done that in other previous years. However, if you do want more information, please come and see Dale on our stand, and we'll be happy to go through that at length. But as with the trial plant from the previous presentation, it's got all the poly makeup unit and feed pumps in there as well. So it's just a plug-and-play unit. However, on Corby in particular, they couldn't get a local power supply, so they had to bring in a generator, which was fine. And they didn't have any potable water for poly makeup. However, the FE provided on site was quite good according to the customer, but it turns out it was quite good, and they didn't have any issues with the Y strainer protecting the poly plant from blinding up. So it was good quality, to be fair. You probably can't make that out, but the little light blue rectangles, our unit, and the two circular tanks just above it are the thickened sludge tanks. So we were taking from one of them. However, and that was the primary goal was processing that pre-thickened sludge, as I said earlier. However, as you'll see, we did, while the unit was there, look at other possibilities, and that was also taken from the feed tank, which is a smaller tank in the upper left corner, and that's where the pre-thickened sludges go. So that's both the Calnus and the SAS. I say this was mid-pandemic, so that did give us some logistical challenges, and as well as having to bring in the generator, they had to hire in a lot of pipe work. So that meant, unlike having a long-term trial, there was obviously going to be a cost associated with keeping that going on and on and on. So that came into play, as you'll see. Filtrate, that was the easy part of the trial. That just went back to a local ground drain, back through the head of the works. And the cake wasn't too much of a logistical issue. They basically brought up a digger with a tipping bucket, which, whenever that was full, that was transferred over to a local cake bay for subsequent removal from site. But it did mean that every now and again I had to make sure I knew where the operator was, so I could call him and say, "Excuse me, sir, I've got too much cake, can you please get rid of it for me?" You probably can't read that, but this table's the main crux of what Anglian Water we're looking for. The rows that are highlighted in different colour are the main areas that we mentioned earlier, i.e. was the pre-thickened sludge too thick for us to dewater without having to mix it down further or dilute it. The active polymer usage there on the second purple row, and in green the cake dryness we were getting, i.e. the stackability and things like that. But also on there you've got other settings like the inlet pressure, the duration between washes, and the instantaneous and net solids capture rates, which is obviously your filtrate quality. To summarise that, although I'll say a bit more about it later, running at full capacity, that's with the auger at virtually 95%, that produced an average cake of just shy of 22% dry solids content, which was pretty good and definitely stackable. And although we did get various polydosing rates tested for just 5 kilograms of active poly per ton of dry solids, that gave us an excess of 21% cake and a net solids capture rate in excess of 98%, which is obviously pretty good. So the customer was obviously quite happy with that. These other things that we trialled while the unit was there, so this was the mainly raw SAS, i.e. just the SAS that had been manually decanted and pumped across. And when I say mainly, that's because there was always going to be a small depth of historical sludge at the bottom of the tank, so I couldn't say for definite this is 100% pure SAS. In terms of the actual depths, there's about of a 4.8 metre depth tank. the bottom 0.7 would always have some historical sludge in it. Thank you, kind sir. So really, this was of interest, and we did include looking at potentially dewatering, either in combination or isolated the two raw sludges. But as I say, the focus was mainly on the pre-thickened combined sludge. So I'm not going to dwell on these because what you can see, we were doing quite well. We were getting around 19% cake from it, which isn't bad for a SAS, but we're pretty sure we were probably underdosing the polymer, and that's largely because of the variability of the feed thickness. You can see there it was around 2.2 at one point and 3.5 the next, so unlike the pre-thickened stuff, this varied quite a lot in consistency. And then we had mainly the raw calmness. Again, we're still at the same issue with the bottom part of the feed tank having historical sludge in it. And as I said, it's very different to typical primary sludge. As I say, it's more like a secondary sludge. You can see that by the sort of dry solids you're able to get in the keg. Yes, slightly more than the SAS, but still around the 20, close to 21% mark. But it does need obviously less polymer. And then this, I really won't dwell on this because this was a bit of a farce, to be honest. Bearing in mind that I live in Bristol, so it's a bit of a hike to get over to Colby, and we'd made plans to try and do this, so say 50-50 split of the pre-thickened, the non-thickened calmness with the SAS, and we were hoping to get a rough 50-50 mix. But owing to possibly a miscommunication, possibly because the site operator who was on duty wasn't listening, who knows. But rather than having 50-50, we think it was probably more 90-10 in favour of the coldness. So, yeah, I wouldn't pay too much attention to this. We were using more polymer for sure, and we were still getting about 80-90% cake, but without that certainty as to what exactly we were testing, I wouldn't put too much focus on this. And unfortunately, this was at the last stage of when they'd envisaged having to keep all the temporary kit hired onto, and to retest this would have meant adding another week's worth of generator hire and pipe hire. So as this was a nice to have, the customer and ourselves naturally made that decision not to keep the cost going. And also at this point, we'd also had the results back from the pre-thickened stuff, which was obviously very favourable. So yeah, this just reiterates what I've said previously, so I won't go over it again. But we were clearly getting a nice stackable cake, 21% or above. We're getting a nice clean filter rate, 98% solids capture rate, and typically an active poly usage of around 5 kilograms, which is nice and low. See, it did it when I wanted to that time, and that's what the cake looks like, and you can clearly see how stackable it is. And it didn't smell as well. Well, it did smell, and bear in mind my sense of smell is obviously gauged from 2 decades of working in the industry, but I'm fairly sure comparably, it was a nice smelling sludge. I say we did test the unmixed raw sludges, but and we did get the stackable cake. But when we started doing more cost analysis, it was clear that we probably were, the customer wasn't going to go down that route anyway. So what we looked at when we looked at the combined cost of power, poly usage, product disposal, and maintenance, they were looking at either do nothing, so just carry on doing as they were, add an acute press after the existing gravity belt thickening, so keep the thickening and then have dewatering after that, and potentially replace everything, get rid of the thickening plant and just dewater only. But as I mentioned before, when they looked at the numbers, by adding dewatering to the existing thickening plant, you were looking at a saving of over 50% compared to doing nothing. And this even went up by almost 5% if you enhance the nature of mixing the dilute poly into that particularly thick feed sludge. As a lot of you are aware, sometimes if it's particularly thick, or if you've got an awkward THP digestate, for example, you sometimes need enhanced mixing and dilution setups. And just because of the feed thickness alone, I think this potentially would have benefited from that. But even without it, we were getting over 50% cost benefit. Whereas replacing everything with dewatering would only have been a saving of around 47%, which is still obviously very good, but the path of least resistance was obviously just to add dewatering after the existing thickening. So naturally it was deemed a success. I've got a nice glowing testimonial there from the poor guy on site who it was basically the site controller who was heavily involved physically in setting up the temporary pipework, and the poor guy, he had to undo a bower coupling while it was still pressurised, and he got totally soaked in carbonate sludge. And I've been the, caring humanitarian that I am, ran over with a blue roll, whereas his site operators were rolling around on the floor laughing themselves silly. So I think that got me some good brownie points. So at present, investigations into other small raw cake applications are ongoing, and a full-scale dewatering installation is currently designed. And in particular, we're reviewing the requirements for an external installation rather than an in-building installation.
Yeah, and that really stems from the unfortunate incident at Avonmouth. It's really focused people's attention around DSAR, but due to that, again, I think what our client told us was that the cost of the building has escalated due to that incident. The figure I was given, something like £400,000 to build a building to the latest standards. So what we're doing is working with them to develop. Sorry, Jeff. We're working with them to develop a system where we can put the dewater outside if necessary. To us, it's still a last resort and something we'd rather not do. But we're all getting challenged with budgets and spends and things like that. So if we can do it where it is absolutely necessary and there isn't an existing building, that's where we're going.
Unfortunately, I've lost the last slide, but it was basically an acknowledgement to the Anglian water staff who were very helpful for the trial, and ask if there are any questions. Thank you very much.
Thank you, Jason. So, do we have any questions?
Excellent.
We don't. You're going to get away scot-free then, gents. We're going to break for coffee now. Back here in half an hour, please, for the final 3 presentations. Thank you. Okay, everybody, welcome back. We're going to kick off again so we can try and keep to time. So those who want to flip between the two rooms can do so. So we've got 3 presentations leading up to lunch. The first one is more volute. So I'm going to let Robert take you away. Thank you, Robert.
Thank you very much, Jeff. Good afternoon, everybody. Thanks for having me here. You already got a little bit of a taste of the volute in the presentation before this by United Utilities. I'm going to tell you about a new volute, the volute Duo. And what this technology allows us or enables us to do is to offer you the same benefits that we already do with screw press technology, but we can widen the application range and we can reduce the amount of wearables for this. So what I will tell you is I will give you a short introduction of the company Amcon, where we're coming from, where we started, where we're going. Then, though some of you already had this short introduction into screw press technology by United Utilities, I will give you a quick rundown on how it functions, especially so I can then tell you what is different with this new technology and how that functions. I'm a service team manager at Amcon. My team is responsible for pilot testing, commissioning, R&D testing, technical support. So in that sense, we do a lot of testing, or my team has done a lot of testing with this technology. And I think it's very interesting for you to see a couple of the results of these pilot tests to give you an impression of the scope of wastewaters we can treat with this thing. And then at the end, I will wrap up with a very brief conclusion, generalization of what you can expect. So, Amcon was founded roughly 30 years ago by Mr. Sasaki. He was working as an operator in a wastewater treatment plant. He saw screw press technology. He saw it didn't work. It kept on clogging. It needed a lot of water. So he came up with the moving ring principle. That's what Amcon started like in '74. Ever since, the screw press technology has remained at the core of what we do. We made some ventures into sludge drying, into polymer preparation systems and the like, but the screw press technology is and remains at the core of our company. I put a couple of iterations, so to say, on that we had. On our website, you can find many, many more. It's like a museum. For the keen observer, you can already see in 2004, we were doing something with 2 screws inside for very particular applications. Then the principle of operation. Screw press technology works by conveying solids through a cylinder. And so you get flocculated sludge coming in on one end, you have the dry cake coming out on the other hand, and the screw conveying these from one end to the other. And in the meantime, of course, you have the filtrate coming out just under gravity and under pressure that we generate. The difference with traditional or classical screw press technology is that we don't use a filter mesh around this cylinder, because the filter mesh keeps on clogging and you need to keep it clean. What we have is a self-cleaning filter mesh. We make this filter mesh by stacking fixed rings and moving rings on top of each other, with a spacer in the middle, of course. And the screw agitates these moving rings, and you can imagine that then the filter gap is constantly moving against each other, which keeps the filter mesh clean. So it's very, very stable. It's a very unspectacular technology if you from an engineering perspective, but the results are fantastic and very reliable, high reliable in operation. The benefits might be already obvious. Like whereas a centrifuge, and for your information, we typically compete with centrifuges and the belt presses, which perform very similar functions with similar results. But the benefits of the screw press technology is that we have a much, much lower energy consumption. You can imagine that if you use energy to convey this a couple percent of solids in the wastewater and to compress them, it takes much less energy as if you would have to use energy to spin this whole bulk of wastewater around at a couple thousand RPM. So that's the first and very obvious benefit. And as you could see already in the long-term pilot test that United Utilities did at the Davy Home site, this can go up to 84%, though I know sites where we were able to save up to 95%. Because we have the self-cleaning moving ring technology, we can do this without much water compared to some technologies, belt presses that use a lot of washing water. We can save really up to 99% in extreme cases. Further, our technology works at roughly 0.5 to typically, 7 RPM. So it wears down slow, it breaks. If it breaks very slow. Maintenance is very plannable. You see it thousands of hours in advance when something is necessary. It also means that it doesn't break spectacularly. In all my time in my current role, I've seen it once that a machine of us broke down to such an extent that we couldn't keep running the machine. That means that operational reliability is extremely high. It also means that this thing can run without an operator 24/7. I don't know if it's the official maintenance recommendation that we give, but it's like, look at the machine for 5 minutes a day, and that's it. So last year I was in our most remote installation, which was in the utmost part of Finland, where one of our volutes has been running now for 13 years without any noticeable service. A bit of an extreme case, of course, but because you can extend the operation hours, because you don't need an operator to constantly keep looking at it, you can also downsize the machine that you need. Good to know for the operators as well, low RPM is low vibrations and very low noise. I would almost dare to say that if we would have the biggest machine that we have, and we would have it here in the place of Joff, we would actually still be able to do this presentation without a microphone. It's really incredible to have this low level of noise. But I'm an engineer, so I can also admit to you that screw press technology is not for everyone. It's not for every wastewater. And screw press technology typically suffers when you have a high fiber or high inorganic content in the sludge. And there's not really a fixed limit, but I would say that from 20% fibers or 40% inorganics, we need to start thinking, do we need to adjust our cylinders or can we go still like this? It doesn't mean that you need to adjust, but you should start thinking about it. And the higher these numbers are, the more adjustments are necessary. And we have units that run on 70% inorganics. It is possible. The problem or the challenge is that these adjustments typically eat away on the benefits that I just mentioned. So, and of course, at some point you have a economical or a practical level where we just say, very sorry, but this is just not something for screw press technology. The way how these things actually are a problem for screw press technology is that they block the cylinder. What inorganics typically do is that they increase the pressure because inside the cylinder, and they wedge themselves in between the stationary parts and the screw. The same thing with the fibers, and there is an interplay between these two. So what you here see, this is what happens if a machine blocks, and if the sludge sticks to the screw and just starts to co-rotate, there's nothing going through, so you don't have any throughput. And the only basically solution for this is that you take the screw out, clean it, put the screw back, which is something we don't want to do. So we call ourselves the screw press specialist. We get a lot of the technically difficult wastewaters sent to us. And we noticed that for some customers, we unfortunately we had to say no. We couldn't do their wastewater until now. Because what we have is the Volute Duo. This offers the same benefits as we had before, but we can now also apply this on these difficult wastewaters. And the difference between the single screw and the double screw technology is obviously that we have 2 screws. We have 2 screws in one cylinder, and the screws of these flights actually turn into each other, meaning there's no space for any blockage to happen, or if it happens, it's simply pushed out. The second difference is that we have an externally driven moving rings. If you remember, I told you that these moving rings are basically pushed up and down by the screw, by the flights of the screw. With this new technology, we have a separate motor for that. And this helps in a couple ways. You don't have the screw to ring contact, so it also reduces the wearables, but it also helps to prevent the blocking because there is no, the solids cannot wedge themselves in between the space of the screw and the moving ring. And then the third thing is the double cutting. It's a bit of a difficult to explain, but basically the pattern in which the rings are moving, on the one hand gives the cake something to grab on so you can push it, you can exert some pressure, and on the other hand, they keep cutting into the cake, which allows more area where you can actually draw the filtrate out. And here you see just a cross-section of the Volute Single and the Volute Duo. So you see the 2 screws running into, or like in between each other, with the externally driven moving rings. All right, so I want to present you with 5 sort of exemplary sludges. It's definitely not an exhaustive list of what we now can do with this technology. And it's the number of tests that I can present to you is too small, and the tests are not super comparable to each other because they're all the complex wastewaters that I can give you nice averages or nice graphs. I can give you the screenshots from the pilot test reports to give you an idea of what is possible. The first one we did in Czech Republic, where we are located with our office. It's a chemically precipitated sludge, inorganic content between 80 and 90%. And as I said, we actually had a normal volute running on this sludge, but we had to adjust it with special moving rings, a different motor, and we couldn't exert the pressure on the sludge to get a nice dry cake. We went in with the Duo, and it actually worked fantastic. It's just something, when you know you cannot block the cylinder, you can really push the machine to its limits in order to try to get the driest cake. Slight side note on this one, we couldn't actually totally push the machine because the customer had a very strict phosphorus limit in the filtrate. So 3 ppm was the limit, so we had to limit the pressure we wanted to put on the sludge. And for your information, all the pilot tests were done with an RVP 241, which is our smallest model for this technology. Throughput ranges from 10 to 50 kilos per hour. And you see here the dryness and the throughput mentioned. To give you an idea, pilot testing, you try to optimize for different scenarios, so maximum dryness and the best overall. Excellent capture rate as well, but it was also necessary because of this phosphorus removal. The second one is actually when my guys brought back the cake, I thought they were playing a trick on me. It's from a plastic recycling plant. They shred this agricultural plastic. They have a duff, and then this sludge went to our machine. The stuff that comes out of this is so rock solid hard. It's not necessarily super dry, but somehow the interplay between some soil, some sand, and some plastic really makes this into a brick. The whole factory, it was actually quite difficult to test because the whole factory, that they made for this is struggling with this particular sludge. The fibers somehow wedge themselves into any space between a moving object and a stationary object. So, for instance, impeller pumps, it takes them 5 minutes to block. Our standard volute, it took them 2 minutes to block, and there was no way that could ever work on this sludge. But with the RVP, absolutely no problem. So here as well, minimum flow and the maximum flow. As I said, the number of test runs we could do on this was rather limited because the sludge supply was a bit of a challenge. The third one was from Sweden. And what you see here is that it's not so much the limit, like the total amount of inorganics and fibers that's a problem. Because if you look at this, like 11% inorganic, 29% fibers, it's not something that you would be super careful with if you read this on a screen. But somehow this plant, it was a paper mill, or it was actually a factory that was making the paper pulp for the paper mills. They had at least 5 technology providers on site, and none of them achieved any measurable cake. Every machine would just clog up super fast. Again, the RVP managed, and the stuff that comes out here is really like, it's this soft board. If you put soft board in a glass of water overnight, that's the cake that came out here. And you also see the capture rate of 99 to 100%, which was incredibly nice. Added advantage for this customer is that we tried, they had a duff and a belt press. Belt press was using 50% of its throughput as heated, pressurized washing water to keep the belt from unclogging. And we used no washing water whatsoever, 0. And moreover, we could actually work with the sludge that was going into their duff. So they could replace the duff and the belt press by a single technology that uses less water and less energy. Here again, some numbers. I think the slides will be shared later, so you can have a look. I think this is especially relevant. I hear a lot about digested sludge on this conference, logically. This was a mix of digestate and SAS, or VAS, as we call it in Czech Republic. Again, not too crazy content, but very big fibers, because there was also, they were using the process water was going there. Also, the stuff that they were cleaning the cars that brought in the cattle to be slaughtered. So a lot of big particles. Again, no problem whatsoever. The existing volute on this side, again, it is possible, but it had to run without any pressure of the sludge. So the dryness was just, I don't know, it was like 10, 12% that we could achieve there without blocking the machine. With this, you can actually squeeze it and achieve much higher values. Then the last one, a meat rendering plant. Probably the nastiest smelling place I've ever been to. They shred cows and horses here, and it's in Sweden, so they go in as one block of ice. It's really interesting sight to see. Very sticky sludge, and I think this is also a nice benefit that we as Amcon can provide. This customer got a very sudden legislative pressure, let's say, to do something about their wastewater. We got this machine there within a week, and they rented it for a couple months before they could solve the wastewater problems. And it's something that we quite typically do. So it's not too difficult sludge, except for that it was very sticky, but we managed to work with this without any problems. It's getting a bit repetitive, I'm sorry, but it's just we don't have any problems with this technology so far. So this is my conclusion. I may be a bit too much of a specialist and a perfectionist to be able to give you nice, general, glossy summaries. But I think that in general, overall speaking, we can say that the difference between a single screw and a twin screw There are basically three scenarios. The first one is that they both perform at the same rate without any problems. And then it's really up to the customer which technology fits better to their needs in terms of investment and the sludge requirement. The second scenario is very clear. Sometimes screw press technology or standard screw press technology just doesn't work. And you have one option, you can go for a screw press of the volute duo type. And this is exactly the thing that I mentioned. We can now extend our range of applications to these complex wastewaters. And the third scenario is when the standard technology actually outperforms or the other way around. And then it's really just do a test and you know which one fits your needs the best. So as a conclusion, we can offer now the same benefits that the screw press offers in a wider application range. We're insensitive to fibers and inorganics. And a further benefit is this, that because we have no contact between screw and rings, we actually reduce the amount of variables significantly. So that was all I wanted to say. I wanted to thank Evergreen Water Solutions. They're here. They did a tremendous job together with United Utilities and their long-term pilot testing. They're downstairs. Visit them. They have a volute cylinder lying there. They can explain you everything. They have brochures, and we're more than happy to talk to you there further on the details. But for now, thanks. If there's any questions.
Okay, thank you, Robert. Time for any questions, if anybody has any. Can somebody take that gentleman a microphone, please?
Yeah.
No. You're going to get one.
Right, okay, apologies. 100% capture rate, that's quite a statement to make. I've never seen any technology deliver a 100% capture rate. And I've been around and I've monitored your trials that you've done in the past with volute, and I've never seen 100% capture rate. Is that specific to the duo? And, sorry, I'll ask the next question as well. Have you got a duo in the UK that we can trial very quickly?
On the first question, no, that's not specific to duo in the sense that on a normal volute, we wouldn't be able to run this sludge. So I think it's specific to the sludge, and this sludge can only be treated if you want to have screw press technology. Well, this sludge can only be used with a volute duo. So in that sense, sort of indirectly, yes, it's related to the to this particular technology. And on the second one, Evergreen is your man to go to, and we can supply quick activities and quick machines. Yes. At the moment, I don't think so. Or no, at the moment not. But it takes 2 days to ship it here, right?
Okay, thank you. Any more? Oh.
Sorry, Leah Abdu, Atkins. In the third scenario you showed there, you advised that the normal volutes in certain scenarios was better than the duo. What could you explain what scenario that was?
I meant it meant it's either the one outperforming the other. It was a bit complex to get it in one picture, but so there are scenarios where one technology outperforms the other, and to be honest, I'm not sure what kind of mechanism is behind this. So I'm not sure why the one or the other would be significantly better. It's always a small difference, it's a couple percent, but we tend to see that that this is there. But for now, I need to say that I don't know.
Okay, time for one more, if anybody would like to ask one. No? Okay, then thank you, Robert. Thank you very much. So, next up, I have a good friend of long standing, AJ Nair, and he's going to talk to us about MicroV. Thank you, AJ.
Thank you, Jeff. Oh, awesome. Really great to be here. Thanks for everyone for your time and attention. Luckily, last year we were able to present at the virtual conference on some of the pilot work that we've done in sort of preparation for this particular project. It's great that I'm able to present, despite some of the issues that we had with COVID restricting travel and our ability to get to site, that we have commissioned our first full-scale biocatalyst plant. I'm going to talk to you a little bit about what biocatalysts are. I'm not sure if anyone came to the European Wastewater Management Conference where I talked about it, but I'll go over it again in a little bit of detail, and then talk through some of the results and outcomes that we've achieved through using this particular technology for the first time in wastewater, not just in side stream, in terms of its performance in delivering the client's requirements of reducing the ammonia concentration being fed back into their plant. So, just a quick one about Microvi. So Microvi's philosophy is that we densify microorganism concentrations inside a reactor to intensify the reactor removal capacity. What that means is we can choose better, more efficient, more effective microorganisms, capture them, and then place them inside a reactor for beneficial use. How we do that is we create what we call a microenvironment that manipulates the beneficial behaviors of that organism. One of the benefits that we get from a mobilization of bacteria in this application is that we don't produce biosolids, which is quite a controversial thing to say at a biosolids conference. But in terms of the way that we harvest organisms in their stationary phase and put them together as a single culture means that you don't actually produce a continuous need to grow within the biocatalyst itself. So as a consequence, whether it be in wastewater treatment or in this application, which is liquor treatment, we don't see a net production of biosolids across the biocatalyst, which can have some significant benefits in terms of OPEX costs as well as other areas. But because of this microenvironment that we produce, we also create a protective environment for those organisms, which makes them a lot more resilient to macroenvironment changes. What I mean by macroenvironment, things like toxic events, changes in dissolved oxygen, changes in pH, which means that you have a much more resilient process by using this particular mechanism. A good example of doing that is that in wastewater treatment, if you get a high saline intrusion coming in, for example, an osmotic shock, because they're protected, they'll be able to prevent that from they'll be able to reduce their activity in order for them to be able to compensate for that particular saline intrusion. What it does also mean is that now you've got bacteria in your pocket, which means you can apply these organisms in any location within your process that you want to, which opens up some versatility and a lot of optimization opportunities associated with that approach. I'll discuss that a little bit later. But it also means that we can select for new organisms. We're doing a little bit of work with a university across in Asia who've identified a new organism which doesn't produce nitrous oxide while simultaneously removing nitrogen from wastewater. That's quite an exciting prospect for us. The issue they're having is they can't deploy it because it's outcompeted by normal organisms. We're able to solve that particular problem because we create this protective environment. We call it micro-niche engineering because effectively what we're doing is we're engineering the habitat around that bacteria, 1 to 2 microns around the cell wall, and that's what's very unique about this technology. Just a kind of a graphical representation. Effectively what we do is we target those organisms which are better, we create these biocatalysts. I mean, it looks like a tic-tac. It's probably a good way of describing it, with the consistency of a Haribo sweet. It's squidgy. The inside of the biocatalyst is quite a complex structure, and it's very unique to a particular organism. What we do is we establish the perfect requirements for that species to be able to flourish, and that takes a lot of effort. So that's where our intellectual property resides, in the material science, to create this very, very intricate habitat for that organism. Just having a quick look, as you can see, it looks a little bit like Swiss cheese. Inside is one way of describing it. It's the ideal environment. We create the material science properties for that organism, for that biocatalyst, for diffusion kinetics, so they're optimized, so we don't get any resistive impacts as a result of diffusion in and out of the biocatalyst. As I mentioned, we use a high density of a particular organism, and it's not specific to a pollutant, it's specific to a process application. So for example, we have a biocatalyst that will do both COD removal and ammonia removal. So you don't need to swap and change depending upon your wastewater. It'll cover most conditions. And as I said, it's a single species. We don't use multi-cultures inside our biocatalyst. What that means is you get some interesting behaviors such as quorum sensing, which is communication between cells, which is also part of that improvement against toxicity and resilience to environmental changes. All in all, as a consequence of doing all this, we can intensify any given process and improve reliability. Just a few points of clarification, because these are questions I get asked all the time. The biocatalyst is not a biofilm carrier. It's not like a moving bed bioreactor where you form a biofilm on the outside. All the work is conducted on the inside of the biocatalyst. A few other things, there's no solids recycles in normal applications, and we don't need to continuously add biocatalyst. It's not a bio-augmentation process because the biocatalyst is retained inside the reactor at all times. So once you add that biocatalyst, it's there forever, although there is a lifespan of about 8 to 10 years. So, pressing buttons. Here we go. Some of the applications that we do cover, and I'm going to focus on the bottom one, but we can cover everything from tertiary wastewater treatment through to secondary and secondary hybrid. Interestingly, in the secondary mode, where we're using a single pass system, that's where we don't produce biosolids. However, if we utilize it as a hybrid mode, which is we combine it with activated sludge, for example, we can actually produce more biosolids. And that's beneficial if we're producing it with a high calorific value, which can produce more biogas. I think we heard in the plenary talk this morning about the importance of biomethane production. In this mechanism, we can achieve the higher levels of nitrogen removal that we are being asked to do, whilst actually improving the biogas production rates. So that's actually a win-win situation for the technology. But in sidestream, we're focused very much on removing the ammonia that's returned back to the head of the works and trying to remove that in an efficient and effective way. And we'll do either straight ammonia removal or we'll do full nitrogen removal. So I'm going to talk about the case study, the commissioning of our first full-scale installation. It's actually in California, a place called Oraloma, which is just outside San Francisco on the other side of the bay. This was a works that treats about 20 mgd, which is around about 70 megaliters a day. So that's considered to be a small to medium-sized works in the US. The reason why they were looking at this technology is because they were upgrading from a carbonaceous-only works to having to treat the total nitrogen being discharged into San Francisco Bay. So as a consequence, they had a new total nitrogen consent, and they were really concerned about the ammonia that was coming back in their digester liquors and what they could do about it. So we have a very good relationship because they're only down the road from us, and they asked us to come up with some options that they could utilize. So we said, okay, well, let's have a look at that. What are your objectives? And the objective very much was to reduce the ammonia coming back into the secondary works to protect that new total nitrogen consent. This is the first time that any one of the 42 plants in the Bay Area of San Francisco was converting to total nitrogen. So this is very, very important for them as almost a test bed for those other 41 systems that will be upgraded in the future. We initially did a pilot plant, and that was to try and understand the design characteristics, because this is the first time that we were using the biocatalyst in this particular application. We had to establish the control requirements and identify any specific mechanical, electrical, and process requirements. So we started off with the classic lab scale testing, then moved to pilot scale, and then to full scale. I won't go into too much detail about this one because I presented on this last year, but effectively we set up a very small reactor in our labs, and we tested it under various different conditions from different hydraulic retention times. Needless to say, the results were very good, which allowed us to move on to the pilot scale. Just a quick overview of what the influent characteristics were. Fairly typical of an anaerobic or mesophilic anaerobic digester filtrate. Typical ammonia around about 500 milligrams per liter, although it did range between 350 up to about 700. And the alkalinity and the pH was fairly typical. CODs were relatively low, around about 270 on average. So a fairly typical filtrate. So we did a pilot scale test using a relatively small reactor, 500 liters, there or thereabouts, and we tested it at different hydraulic retention times and packing densities, and we did some stress testing as well. Just some preliminary results. Like I said, this is not the basis of the presentation, but here we can see that during the testing, you can see ammonia in the dark dots in the influent and ammonia in the effluent in the white dots. And as you can see, as we progress through lower and lower organic loading rates, you could see the improvement in ammonia removal. And actually at 0.9 kilograms per meter cubed per day of loading rate, we were achieving around about 95% ammonia reduction. What was very interesting was this organism, which normally goes to nitrate, was actually only going to nitrite. So in that instance, it was using around about 25% less oxygen to do so, but also conversely, when it passes through the main works for it to be reduced to nitrogen gas, it will use around 40% less carbon. So a reduction in operating costs as a consequence of this approach. Now that's quite unusual because it's very difficult to move away and prevent nitrate being formed with this particular type of process. So we moved into full-scale implementation on the basis of the pilot results were very, very good. So we looked to see what we could do with existing assets in order to be able to reduce the cost, given that this was a first installation and there was a high risk associated with it. So we thought, how can we reduce the cost? We did two things. A, looked at repurposing some existing assets, but also obtained a grant from the local EPA, who funded 50% of the project, whilst the client funded the remaining 50%. That's actually quite unique to the US in terms of how they look to implement innovative technologies into the marketplace. What we did is we took an existing 340 meter cube tank that was available on site. We had to line it with an epoxy coating to reduce the abrasiveness of the concrete, which would have broken down that Haribo squidginess that I talked about. We reused an existing blower from site. This was a blower that was left over from the total N conversion. And as a consequence of being limited to that particular size, that's what dictated how much ammonia we could remove from that reactor volume, not the available reactor volume itself. So by repurposing that, we're able to reduce the cost. We're also able to use magnesium hydroxide as an alkalinity source, which was, again, used on the main works. And we use what we call the quiescent zone, which I'll show some pictures of, on retaining the biocatalyst in the system. Why that's very important is that these biocatalysts are typically 5 millimeters in diameter. If we were to put a sieve system in there, it would foul within minutes. But because these things settle very quickly, we're able to use a stilling well, for all intents and purposes, to be able to retain the system, which takes away any issues of fouling and clogging. We did have to include spray nozzles because, like any filtrate with residual polymer in there, it's likely to foam. So look, it's a big box with some air being blown into it. There's not much more than I can say about it. We're taking influent coming in around about 200 kilograms per day, and we were looking to remove between 80 and 90%. Here's some pictures. These are the diffusers. That silver stainless steel system is the quiescent zone. It's just a very straightforward stilling box, which is used to provide a zone of no mixing that allows biocatalyst just to settle out and be pulled back into the main reactor. Therefore, there's no chance of any clogging or fouling. As you can see, it was an existing tank, so it had some very interesting architecture for us to work around while we're installing these retrofits. There it is in action. It's a tank with some water and some air going into it. Now, this is the more important one. Here's the results. So we started commissioning in May. The red line here is the influent ammonia. The yellow line is actually the ammonia load in kilograms per day, and we're slowly ramping that up over a period of time. The reason we were doing that is, if you notice, the ammonia concentration has been coming down. As a result of the operational changes that they saw by moving to a total N sludge, they saw a decrease in ammonia concentration coming through. But as a consequence, but even with that lower amount, and we had to increase the flow rate to the works to compensate to achieve that loading rate, we were able to get ammonia levels around about 50 milligrams per litre coming out of the system. When we look at that as a load applied to load removed, we were starting to move towards almost 80% reduction, which is what we were looking to achieve. And as you can see, as we ramped up the load coming in, that load removed also started to increase as well. Just having a look now at the sort of the asset, the piece around the nitrite and nitrate formation. What we have been seeing is a little bit of variation in the full-scale plant between the nitrate and the nitrite that's forming. We're starting to see around about a 50-50 nitrite to nitrate ratio. We're going through an optimization phase at the moment while we're trying to reduce that. One of the reasons we believe so is because in the full-scale operation compared to the pilot scale, we're only running around about a 5% packing density, which means 5% of the volume that's occupied of the reactor is biocatalyst. When we did the pilot study, we were around about 15%. So the actual biocatalyst is performing much better in this application than it was in the pilot scale. So we're in the process of optimizing that right now to see if we can drive more nitrite rather than nitrate coming through. And then if we look at the dissolved oxygen, as I mentioned, we sized this plant on the peak capacity of the blower. So we were expecting the blower to be operating at 100%. What we're actually finding, even the blower operating at 50%, so about 2/3 of the actual airflow rate that we expect to see, we're still achieving dissolved oxygen concentrations of around about 4.5 to 5 milligrams per litre, which shows that we've actually got a higher oxygen transfer efficiency in the system that we anticipated, so that reactor can actually take more load. So part of our work going forward is to actually start pushing more and more ammonia through the system. So those loading rates that we had of 0.9, we think we can actually push much further than we previously thought. And then when we look at the actual power consumption, because I think that's quite important, at the moment we're averaging around about 2.6 kilowatt hours per kilogram of ammonia removed in the system, which is pretty good, and we're going to look to optimize that further. The client had a target of around about 3, so we're beating that already, but we're going to try and get that down to 2 kilowatt hours per kilogram of ammonia removed, simply because of the fact that we want to try and get as a lower energy consumption as possible through the thing. And I think that's pretty much what I wanted to say about how that system is performing. So what we've seen is that in this first application, the ability to apply a very simple, straightforward technology which requires very little operator intervention, has no complex control systems, there's no DO control, the only thing that we have is pH on the control system for the mag hydroxide. There's no recycles, there's no redox control, there's no sludge age control. We're able to achieve a very simple process for nitrification or nitritation. No downstream solid separation required. There's no specific process configurations, which is why we could repurpose an existing tank. The depth of that tank was only 3 meters, whereas in most cases you would need about 6 meters to take advantage of oxygen transfer requirements. And we found that during the course of commissioning, with the operations team doing a lot of maintenance work on the filters, we were shutting the plant on and off on a regular basis, and there was no impact on the process as a consequence. So it's very resilient to operational changes. We're presenting a paper at next year's WEFTech, and that's being presented by our client, and the key message that they keep saying to us is, don't underestimate how simple this technology is. For us, it's a fit and forget type technology, which is exactly what they wanted in terms of their operations. So that's all I really wanted to say on the system. I don't know how I'm doing for time, Jeff, but I think I might have beaten it, which is good. So hopefully there's lots of questions. And thank you very much.
Okay, AJ, thank you very much. Do we have any questions? Oh, we do.
No, brilliant.
Would you like to go first? There's a microphone coming.
AJ, it's Richard Smith from Jacobs.
Oh, hi, Richard.
Hiya. Impressive performance in California. How sensitive is it to temperature? Have you thought about applications in this country?
Good question. So just in this particular application, obviously, when you're dealing with anaerobic sludges and filtrates, the temperature usually is quite consistent. It's between 20 and 25 degrees centigrade, although we did see it go up to 30 degrees with some of the California temperatures. So in this application, we know it's generally going to be okay throughout the world. We have tested the same biocatalyst in UK temperatures on wastewater, and we've been down as low as 6 or 7 degrees centigrade, and we've achieved the same levels of performance. So we've just completed a study with Wessex Water, we've done one with Thames Water, and we've done one with Scottish Water on both secondary and tertiary applications, and we have gone down to those low temperatures, and we've achieved, typically less than 1 milligram per litre on a tertiary application, if not down to usually below limit of detection, which is 0.05. And those are all available as case studies and presentations in previous AquaEnviro conferences.
Thank you. Any more?
Hi, Dimitris from Atkins. Just wondering if you have applied the technology on the THP liquors, which has, this is the thing the whole conference is about, you know, to have.
Yeah, it's a good question, and we haven't yet, and we'd like to. So we're having some conversations with Canby at the moment in order to be able to see if we can utilize it on one of those sites to see how it copes with, you know, 3,500, 4,000 milligrams per liter. We think the biggest issue that we're going to find is pumping enough oxygen into the system, into the reactor configuration, and also getting enough alkalinity and getting the alkalinity controlled through it. One thing I will say is that the next step for this technology is the application upstream of Animox. Because if we're producing nitrite and we can tune the system correctly, then it makes perfect sense for going downstream of deammonification.
Thank you. I think there's one there.
Leah Abdu, Atkins as well. I think you advised that you could actually produce more biosolids with high calorific value. How? Was that in conjunction with the secondary treatment, or?
Yeah. So if you understand the principle of secondary treatment, that in order to get a nitrifying sludge, you have to run at a long sludge age because you've got to try and grow the nitrified population. What we're able to do is, because we're now effectively divorcing sludge age from the equation, because you can retain a population of a nitrifying organism independent to the main mixed liquor. So that means you can actually run a mixed liquor at a sludge age of less than 3 days, which means you've got a sludge which is more akin to carbonaceous. So you'll actually have a higher cell yield, which means you produce more biosolids than you would from a conventional nitrification works, and that itself will have gone through a lower level of endogenous respiration. So both the extra volume and that higher level of sort of volatile fraction that's remaining should give you a higher amount of biogas in your anaerobic digesters.
Anybody else? Oh, sorry, you're going to have to walk back across.
It's Richard Smith from Severn Trent Water. So, I'm interested if you've looked at the impact of your technology on process emissions, specifically around this liquid treatment.
That's a great question, and we're very, very conscious of that. I mean, one of the things that we're going to be doing as part of the sort of evaluation of this technology is to see what the N2O emissions are coming off this particular reactor, given that we've got nitrite production going on. Some of the things that I mentioned very early on, the technology can be used to select for different organisms. And we know there are organisms that are out there which will achieve nitrification and denitrification without going through a nitrous oxide production pathway. So indeed, we're putting in one of these Ofwat Innovation Catalyst funding applications alongside Severn Trent at the moment, which is to look at using that particular organism for SND in the system. So fundamentally take away the pathway for nitrous oxide emissions.
Okay.
And the other, in the secondary mode, if you understand the mechanisms of N2O production, part of it is the transient response. So when you take nitrifiers from their aerobic condition through to anoxic and then aerobic again, you have a propensity to generate N2O in that level. If you imagine a system where you're no longer taking that nitrifier through that transient condition because it's always staying in the aerobic phase and never going into the anoxic phase, and that's separate, then you're going to reduce the mechanism in itself.
Okay, thank you very much, AJ.
You're welcome.
Okay, everybody, so our final presentation this morning before lunch is Willie from PAX. Over to you, Willie.
All right, Jeff, thank you very much. I'm glad somebody's still staying here. Please buckle up and enjoy the journey to the past and the present with 20 years of experience with the Animox process, as we have taken that journey all the way. So I hope you enjoy it as well. So it's a kind of celebration because by the end of this year, it's 20 years that the technology actually was developed, and it all started in the University of Delft 20 years ago. Just some discussion about the natural nitrogen cycle. The biological processes involved is nitritation from ammonia oxidized to nitrite and then converted to nitrate. You can denitrify it by presence of CUD, let's say a carbon source, and bring it back to nitrogen gas, and there are biological ways to have nitrogen fixation on that. The Anamox is a shortcut of this process and stopping, let's say, the oxidation to nitrite, and therefore having the potential of saving energy up to 60%. And you talk about, let's say, kilowatt hours per nitrogen removed on design basis of 1 kilowatt hour per kilogram of nitrogen removed for Anamox solely. This is a one-step process. I will elaborate a little bit more about that, because the partial nitritation, so 50% oxidation of ammonia to nitrite, and the conversion of ammonia together with the produced nitrite to nitrogen gas, that is happening in one step. This is done in a granule-based process in which a mixture of various microorganisms are present, predominantly AOB, this is ammonia oxidizing bacteria, who do the partial nitritation, and the Anamox, who actually do the conversion of ammonia and nitrite to nitrogen gas. Now, this is happening in the Anamox one-step reactor. There's many bacteria involved in this whole process, so everything which is now being blurred is happening, let's say, in a wastewater treatment plant. So the nitrogen fixation that's typically happening in soil roots, and you can of course have the Haber-Bosch process to artificially produce fertilizers. But I just wanted to show you, let's say, the bacteria involved in this whole process, as I will elaborate a little bit more on that. So AOB stands for ammonia oxidizing bacteria. NOB is the nitrite oxidizing bacteria, which you want to avoid that step because that's consuming a lot of your air. And you will have the heterotrophs, which are doing the denitrification. How it all began? 20 years ago, actually before 20 years ago, so this University of Nijmegen, they were doing research in the field and coming up with bacteria that actually could convert ammonia and nitrite to, let's say, nitrogen gas. And the air that we're breathing currently is, most of it is produced by Anamox bacteria. Whether you like it or not, it's just, this is what happens before human activity was on Earth. It was with the help of Technical University of Delft that they did the testing in the laboratory to optimize the whole process. And then we went actually to a laboratory scale facility, which were, us as a company were involved. And that led, about 20 years ago, 2002, there was a startup to the world's first Anamox plant built in Rotterdam, still operational. This is a two-step process. That means that the nitritation reactor was already present. That was a Sharon reactor doing the conversion of ammonia to nitrite. So this reactor was only doing the Anamox conversion from ammonia and nitrite to nitrogen gas. 70 cubic meter reactor. Again, this is depicting, let's say, the two-step configuration as it was applied at the wastewater treatment plant of Rotterdam. In a partial nitritation, the ammonia was converted partially into ammonia and nitrite, and then the Anamox transferred it to nitrogen gas. So today, I'm going to elaborate more on the one-step configuration, which is actually the state-of-the-art nowadays. The configuration two-step, you see two examples, one of the reactor in Rotterdam, the other one is a tannery plant. There's typically two tall tower reactors in which the reaction takes place. This is actually nowadays, most of it's been applied the one-step configuration, which is a much more shallower tank configurations, which can be made of concrete or steel or whatsoever. Just some historical background. In 1989, there was a patent being issued by the University of Delft, and us as a company got a license from that. Beyond that, Parks itself we developed new technologies, mainly based on the hardware, but also on the process itself. That led in 2006 as the first one-step reactor, granular-based reactor. That was also in combination with the Struvite reactor technology with Fospac. And in 2009, we have the world's largest Animox plant, which is 11 tons, so 11,000 kilograms of nitrogen a day being converted. 2014, we had the first THP application, which is the plant in Tilburg. And, well, European largest Animox was actually a two-step project, I can say. That was the plant at Birmingham at Minward. We first did a project for Severn Trent, doing a plant for regular mesophilic anaerobic digestion liquors for 4,000 kilograms. And later we did extend that plant with a total capacity of 6,000 kilograms of nitrogen a day by converting existing tanks present into this new reactor systems. Currently, as we speak, we have approximately 150,000 kilograms of nitrogen per day installed, 66 plants as we speak. And the benefits of PNA, that stands for partial nitrotation Animox, combined in one set. You see here as compared to if you would treat these liquors by conventional full nitrification and denitrification. It's the footprint of the reactor systems. It's 10% of what you would have for traditional systems involved. That's mainly due to the fact that we are using very concentrated granulated biomass, which allows us to have small volumes. So we don't compromise on the sludge loadings. We just can allow for more concentrated sludge and therefore for smaller reactor systems. There's no carbon being needed, especially in certain areas like in the US, where there's actually lack of carbon to go for full denitrification. They are adding actually methanol, which is quite a high expense to go for all the way. So there's really a benefit to go the route for Animox. There's the Biosolids production is also 110% of that, and therefore you have savings on, let's say, the amount of sludge being produced, but also the dewatering polymers and the power involved. And also we'll elaborate a little bit more on greenhouse gas emissions. I think this should be your daily bread and butter. I think the sewage treatment plant combined with the anaerobic digestion. Typically, as it's been depicted over here, this reject liquor is not much more than 1% of the total flow of the sewage works and makes up of the nitrogen load not more than 10 or 20% of the total sewage works. Now, if you go for a side stream, you can put there the Animox and treat that liquor and have the savings on, as I already said, the footprint, the energy, the sludge production. The liquor itself can also have, depending what kind of mainstream process you apply, but if you BioP processes, you can also have phosphate being released during anaerobic digestion in high volumes and high concentrations, which could then also be treated into the side stream. Otherwise, you would return that phosphate back to the main works and have to remove it again. So that makes sense. And we also did sometimes, as already since 2006, sometimes certain installations apply Fospac technology, which is Struvite, straightforward Struvite formation, and therefore you make fertilizer embedded with nitrogen and phosphorus, which you can recover. Allowing co-digestion if you have anaerobic treatment. There are plants where there's also industrial effluents being blended into the side stream before it's actually going to the main works. And then we, of course, we have THP, as a lot of discussion has been already during this conference. The THP allows also the implementation of external sludges, as you will have sludge centers that will actually also treat sewage sludges from satellite plants. Again, the flow is not very much more than 1% of the total sewage works, but then the nitrogen load, as I will show in some examples, can make up to 50% of the total sewage works, which is very significant. So these are the potential recovery possibilities if you would go for such a side stream, combining anaerobic treatment. It is, of course, the biogas that you produce. It's common sense. If you have industrial effluents being applied, you can produce granular sludge-based anaerobic sludge. You can have biological desulfurization of your biogas producing a sulfur fertilizer. This is already happening. Struvite, of course, in various forms. You can have a powder form. Some of the plants, they pelletize it and then sell it off. You don't need to do it. There's also plants who are just taking the struvite off, blending it back into the biosolids, and as it is possible in the UK to go for land application. This is not possible in the Netherlands, as all sewage sludges in the Netherlands has to be incinerated. It's just regulations. And then, of course, the Animox, you produce some granules which have EPS potential, but I will not go much more into detail. This is a configuration how it looks like. It's a continuous operated process. It has a biomass retention systems to allow the granules to be inside the system, but selectively wash out any flux. There's fine bubble aeration, and there is an automatic process control, which, yeah, you can go for a very simple process control or sometimes pH only. We like to do a plural, multiple, let's say, process control or more than one sensor parameters, so that we can steer the process very accurately. Some practical examples for those of you never seen the biomass. This is how it looks like. Very different colors and shapes. You see on the edges, you see the ammonia oxidizing bacteria, and inside the granule itself is predominantly well protected from the hostile outside world, I would say, the Animox bacteria. Some other examples, various sizes of granules that you, on completely red, on the left side, you see the two-step Animox, so that's purely Animox. And on the right side, you see examples where the Animox is actually encapsulated, the outside is composed of AOB bacteria. Just some basic examples. The Animox process biologically always produces approximately 10% of nitrate, and that is due to the growth of the bacteria. It's good to have some growth, otherwise you might lose it, but you want to have not more than this 10% of nitrate growth, otherwise you go the route for nitrification, denitrification. So these are long-term data where it has been just proven, let's say, for many years, that you can stay at this boundary or below than 10% of the ammonia being produced as nitrate. This is also done by selective washout of NOB bacteria, which predominantly are present as flux. But as we wash them out in our systems, they don't bother the overall process. The second selection criteria is the granule itself, because we have the substrate gradient inside the granule, and that's actually limiting the NOBs to grow inside the granule, at least because they need high DO and they need high nitrate. And you don't have both of them at the same time. Startup time, the first plant, Rotterdam, took us 3 years, but there was no Animox plant, there was no sludge available at that stage. So that's what happened if you do something completely new. But in 2006, when we did the startup of the first one step, it took us half a year, which is quite elaborate. In 2012, we could do it, let's say, 1.5 months, and in 2019, we could do it in 5 days. Of course, this all depends on the availability of the granular biomass that you can take from one site and bring it to another site and actually do an immediate startup. That plant in 2019 was in the US. Sludge was being transported by ship, on the ship for 4 to 6 weeks, and still we were able to do this startup in 1 week time. Long-term performance, just want to show you the typically results of that between 250 and 2,000 milligrams per liter of ammoniacal nitrogen. That's typically where those plants are operating. What we see with side stream is very often extremely variability in loadings. That's as we have to deal with it, but it's an issue I want to touch base later on again. So despite these enormous peaks, and we're not talking about twice, triple, or quadruple, let's say, the loading rate sometimes these plants have to deal with. And still they perform very well. And if you look at long-term, so these are data from this, the first one is 8 years, 6 years, and 2 years of data results. You see actually that the plant, this is the loading rate on the x-axis as the loading rate being applied, and removed on the y-axis And you see actually we are long-term removal efficiency are beyond, let's say, 90-95% removal efficiency, proven. Despite very extreme conditions to operate on. Experience with THP, we have, of course, the plant in Tilburg. That's the first picture, and the second plant was the Minward plant, which halfway we did the final biomass inoculations, and ever since then, results were excellent. There is a new plant project coming up at Stoke Bardolph, Severn-on-Trent, hopefully at the beginning of next year. And there is a new plant coming up in Hong Kong, which is under construction at the moment. Again, extreme loading rates we have to deal with, and despite of that, the return loads brought back to the main works was of satisfactory quality. Resilience, as already said, we are dealing with a granule, and therefore the Anammox bacteria are well protected inside the granule, and therefore we have seen that was an accident, 1 week long. Hypochlorite was been put into the treatment plant. Of course, hypochlorite is designed to kill. Whatever process, biological process you will apply, it will do its work. And despite of that, the system did self-recover without, let's say, having to reseed the plant. There's also can be, let's say, environmental factors. Let's say there could be variation in parameters like DO or nitrate, but the principle of this granule is actually that you have this substrate gradient and ensuring that you protect the sensitive, well, people think they are sensitive, but actually they are enormously robust Anammox bacteria inside the granule. Impact of micronutrients, in generally, we don't need to apply any micronutrients. However, we do allow to, let's say, do advise to, at certain cases, at condensates, which is traditionally, we have a shortage of salts, and also single-sided AD feedstock. Talk about, let's say, co-digestion, and this is an example where we had excellent results, more than 90%, but then due to the composition, change of composition of the feedstock of the co-digestion, the process deteriorated. Once we found out that this was due to, let's say, a limitation of trace elements available, we dosed it, and then ever since, let's say, that project, and you see this is 1.5, 2 years results, the activity restored. And there are various reasons why this can happen. That can be precipitation of the essential elements, can also be chelated metals by melanoidins, as you might have happen in the composition of THP reject liquors. Now, I come back to this biology. This is those various schemes, as you can find them in literature, where greenhouse gas emission can take place. What kind of biological processes are responsible for that? They're all connected to nitrification and denitrification. They are not connected to Anammox. You can read this. There's even, let's say, the discussion and literature about comparing, let's say, combined nitrification with Anammox. Let's say that's the PNA combined with conventional nitrification, denitrification. In this study, and I'm not saying this is applicable for everything, but there was a significant savings on greenhouse gas emission equivalents in favor, let's say, of the PNA process as compared to nitrification, denitrification. And again, we come back to the nitrogen cycle, and the biological processes responsible is AOB and denitrification heterotrophs, which are present for the full scheme for nitrification, denitrification, and which are not present denitrification for Anammox, and only 50% present for the AOB in the PNA configuration. So actually you can lower your carbon footprint of the plant by adopting Anammox or PNA Anammox technology, because it is connected to AOB and heterotrophic denitrification. There's where N2O emission might occur. I'm not saying it will occur, I will come to that later. But the specific greenhouse gas emission for PNA Animox is in potential much lower than traditional BNR activated sludge going from full nitrification, denitrification. Now, there is also an issue about how to deal with measuring greenhouse gas emission, and that's quite complex. And it's doable, but it's very complex. And what has happened in the past is that very often measurement was done, but only a short period of time, or on a not representative period, let's say period it was done. Or it was done, and it was the conclusions made on that were based and were pinpointed to the process itself. Whereas the statement is actually that N2O emission is more related to the way how you operate the plant than to the type of process. And because with N2O emission, if you have the bugs and the process train in series, if you don't stress them, they do their thing. They produce what they need to do. It's only when you stress them that they have these burps and hiccups, and they might release some fugitive gases. And that's actually what I want to come to. And this is actually a picture which is quite early done at the plant at Rotterdam, where actually the Animox process was compared with the existing Sharon nitration process, and it was just a fraction of the N2O emission, greenhouse gas emission, of the nitration. The thing on the completely on the right, the column on the right side, is the B stage. That's the activated sludge stage at Rotterdam, which was huge greenhouse gas emissions. And again, the Animox process had hardly any. And when I spoke with Professor van Loosdrecht about these results, he said it's not the Animox that actually produce it. What you find, if you find it in the Animox, which is a solely Animox process, is actually the influx of AOBs from the nitration reactor, which still do their thing, denitrification, into the Animox process. You probably can't see it exactly, but apart from the two-step process, there's also a one-step configuration being embedded there, proving again that the potential for PNA, for greenhouse gas, is much lower than for traditional full nitrification, denitrification. But be careful by drawing simple conclusions, as I will also not use that. I will not say this will never happen in our system, because it depends on different kind of things. And the way we have to deal, and I think it's also with greenhouse gas emission from methane, as we heard it earlier, we have to rethink how we're operating our plants. We can push everything through a small unit and have to do everything and have to deal with all the fluctuation. Yes, that's how the approach was in the past. But maybe we should recapture that idea and think how now with the new incentive, new way of thinking, just focus on mitigation on greenhouse gas emission. And then it's actually, as I showed you, enormous variation with side stream leakage you have to deal with. Just mitigate that fluctuation and the bugs will do their thing. And they let them do their thing. Don't stress them all the time, and they will do what you want them to do. And so greenhouse gas emission is mainly only emitted when you have stress conditions. It's like you buy a good car, a nice fuel economic car. But if you have a stupid driver and he pushes the brakes all the time, and then he wants to speed like Hamilton or Max Verstappen, yeah, you're going to have greenhouse gas emission, don't you? I mean, this is obvious. So there we have to learn that it's not only the technology itself, it's also the way you operate the plant, the driver of the process, where we can optimize, and I think where we can definitely mitigate greenhouse gas emissions in biological processes at all. Just to show you some small footprints of 3 plants. The first one is Oldbergen. It's giving you a size of the side stream treatment plant. And the first one is making up 50% of the nitrogen load. And you see how small that is as compared to the main works. And even a part of that main works was taken out of order when the side stream treatment plant was implemented. The second example is Minward, showing you 2 Animox reactors. And you see the area they occupy. There's existing tanks. We didn't change anything, but you see that how that compares with the main works. It's doing 30% of the nitrogen load. That's enormous. The third one is 45% of the load at Tilburg. A small facility can do a lot for the main works of a sewage treatment works, having all the benefits as already discussed. Just some pictures, some final pictures, just to give you an idea. Rectangular concrete tanks, round circular concrete tanks. You can have stainless steel, you can have coated mild steel, you have the one at the right bottom, that's actually the American experience we had. We started the plant up in 5 days at minus 30 degrees Celsius. We were able to do that. The water was, of course, not minus 0 degrees, but outside it was, as you can see that. And there is another plant on the left bottom corner. Is actually the plant is completely embedded inside a building. So there's different way of building these kind of reactor systems in existing structures, as we did it for Minward, as the top right one, but also in new structures. And we can fit for purpose, let's say, on the needs of the customers. In summary, I still have time? Yeah. Okay. As already said, 150,000 kilograms of nitrogen per day treated. I hope I enlightened you that it's a very robust system, having to deal with very high loading variations. We can go up to 2.5 kilograms of nitrogen per cubic meters a day. We have proven long-term removal efficiency up to 90-95%. The concentrated granular biomass is a real asset. It protects you, let's say, from upsets. It allows you to have very compact installations, and it is very tolerant to inhibitors, which might occur. And as we are a little bit into the shitty business, I mean, shit happens, everybody knows that is in this room, so better be prepared for it. And final statement is properly operated side stream P&A Animox can really lower the carbon footprint of the overall sewage treatment works. So you can take off your seat belts, and so I think I'll pass you through safely to this journey in the past and present. And if you have any queries, then let me know. Please,
Thank you very much, Willie. Time for a couple of questions, if anybody dares. Amanda, the lady in the corner. We'll make you next, Amanda.
Sorry about that. I was just quickly looking at your last slide where you state performance in the region of 90 to 95% removal of ammonia.
Yes.
Is that including chemicals, or do you need any additional chemicals or carbon source or anything just to achieve that?
No, the Animox process is using no carbon for doing the denitration, let's say. So there's no carbon source being needed for P&A processes. And sometimes there is not a sufficient alkalinity into the wastewater present, and then you have to make up or add some alkalinity in the form of caustic if you want to achieve higher loading rates. Certain plants don't want that. They're satisfied with the efficiency of 80%, and then because they don't want to add the chemicals, that's fine. But if there is a limitation on the amount of alkalinity present, then you can add that. Yeah.
Thanks very much, Amanda Lake from Jacobs. Yeah, really interesting overview. And I guess my question is around nitrous oxide. In principle, the potential, as you say, is there, but I mean, what we find in reality, you know, for example, for BNR plants, have the only available nitrous oxide removal pathway, but in reality, what you see is when the measurements, you know, and there's not that many long-term campaigns, and we need more of those, but we actually see higher emissions from those plants. And as you say, a well-operated process potentially has the ability to have lower emissions, but the reality from literature does not show that. And I guess that my question is, I realised your recent paper, I think, references a 2009 paper around nitrous oxide, but are you considering working for with the clients to actually measure nitrous oxide and work with them to optimise the process so that it is being run in a way that actually allows for those emissions to be mitigated? Because I think the alternative is that they are actually much higher without that optimisation, which I guess isn't part of business as usual. So are you going to do that?
Yes or no. It's, let's say, in principle, it's not up to us as a supplier to embed this kind of optimization. I think it's primarily our customer base that should have an interest in this. We are just supplying the machinery, let's say so, and we can advise how to operate it. But as I said, you can advise how to operate it. You can say, keep a steady load, but you see what happens in practice, and everybody in this room probably knows, practice is different. So I think the focus should be on, let's say, mitigation on the loading rates rather than optimizing, let's say, trying to optimize on the process itself. You can optimize on it. You can avoid, I mean, there's literature about the impact of flux, there's the impact of fluctuation of DO that has an impact on the NTO emission. But it's difficult to draw a general conclusion from that to the practical situation for new plants, because every case is a little bit different. But it would be very interesting. But I also want to warn, and I've seen also scientific research where people are doing this kind of analysis, doing strange things to the machinery, and then draw a conclusion about the NTO emission. And that's like what I said with the car. If you have the car and you pump up with your gas all the time, you will get what you want to have. So you will rather, I would rather see, let's say, doing the measurement and finding the right tools how to optimize the process rather than connect a certain kind of percentage of fugitive gas emission on a certain kind of process, because I don't believe in it. I think it's much more related to the way how you operate the process.
Okay, thank you. It's lunchtime, so I'm going to draw this session to a close, and I'd like to thank everybody for this morning's attendance. Thank you.